Good day, students. Today the topic of discussion is FAR filter design using frequency sampling technique. The steps involved in a frequency sampling method is initially the identification of the frequency response HD of e power j omega based upon the type of the filter, being it low pass, high pass, band pass or band stop filter. This frequency response is converted into h of k by means of frequency sampling, where omega is divided into 2 pi k divided by n samples, where n is the order of the filter and the value of k ranges from 0, 1 up to n minus 1. So h of k is a sampled version of the frequency response hg of e power j omega, which is nothing but the DFT. From the DFT, secondly, we proceed on to find the inverse DFT, which gives the impulse response of the filter. From the impulse response, we can easily identify the filter coefficients of this filter. Here, we are going to study about the symmetric filter characteristics, where the coefficients are going to be symmetrical about its axis of symmetry. So let us go into the detailed steps involved in frequency sampling method. Step 1, we need to specify the frequency response characteristics Hd of e power j omega, which contains both magnitude and phase embedded within it. It's given as e power minus j alpha omega. So for a low pass frequency response, Hd of e power j omega is given as e power minus j alpha omega between omega to 0 to omega c, where omega c it is a cutoff frequency. Alpha is equal to n minus 1 divided by 2, where alpha is called as the center of symmetry since we are talking about symmetrical FIR filters. So here we can observe that omega c value is the cutoff frequency of the filter, and since it's a symmetric filter, the response of the filter from 0 to pi is symmetric again from pi to 2 pi. This symmetric feature is the one that is exploited in this linear phase FIR filter design. Let us further explore this by taking an example. Order of the filter n equal to 7 and cutoff frequency is equal to pi by 2, which obviously gives alpha equal to 3. So Hg of e power j omega is given as e power minus j 3 omega. The value of omega is from 0 to pi by 2, where pi by 2 is said to be the cutoff frequency. From 0 to pi, the response is said to be 0. So the step number 2 is conversion of this frequency response into h of k by frequency sampling, where omega should be replaced by 2 pi k divided by n. So h of k sampled version is equal to the frequency response hg of e power j omega, where omega is replaced by 2 pi k divided by n. So h of k is equal to, we have seen in the previous that it is equal to e power minus j alpha into omega. This omega is going to be replaced by alpha 2 pi k divided by n for discretized values of k. So when omega equal to 2 pi k by n, the corresponding k value will be equal to, for the particular omega, the k value will be equal to omega into n divided by 2 pi. The transformation from omega plane to k plane for the example given over here is considered. So hd of e power j omega equal to e power minus j 3. Omega is replaced by 2 pi k by 7 as inferred over here. And each value of omega is 2 pi k by 7, 0 to pi by 2. Again here the response is 0 from pi by 2 to pi, and omega is replaced by 2 pi k by 7. Further simplification gives e power minus j 6 pi k divided by 7. The value of k, if you simplify, just cross multiply, we get 0 to 7 by 4. And again greater than 7 by 4 and lesser than 7 by 2. The value of k is an integer and it should be discretized. And hence, we start with k equal to 0. Lesser than 7 by 4, 1.7 lesser than 1.7, the discretized value is taken as 1. Greater than 1.7, the discretized value is taken as 2. And 3.5 lesser than 3.5, the discretized value is taken as 3. Hence, the sampled version of frequency response h of k is given as e power minus j 6 pi k by 15 for k equal to discrete values of 0 and 1 and 0 for 2, 3. The magnitude response of this h of k is given by, when you take the modulus of e power minus j by applying Euler's property, you obviously get the magnitude response as 1. So kindly note that modulus of h of k is the magnitude response of h of k. To put everything in a nutshell, hd of e power j omega is a frequency response. H of k is a sampled frequency response or DFT, which is obtained from this frequency response, which is what we have calculated in step number 2. Modulus of h of k is a magnitude response of this h of k. Also, an important point is this frequency response also contains a phase component. That phase component is given as minus alpha into omega, which is nothing but we have e power minus j alpha into omega. So this alpha into omega is nothing but the phase response. So you can observe that the phase of the filter is linearly dependent upon omega. And hence, this FAR filters are called as linear phase FAR filters. To give an intuitive idea of how the transformation takes place from omega to k, we can see that this omega ranges from 0 to 2 pi, which is continuous, given by the blue line. Now, we are discretizing this omega for different values of k. For order of the filter n equal to 7, we are taking k equal to 0 up to 6. So for each value of k, the omega plane is discretized. So for each value of k equal to 0 corresponds to omega equal to 0. K equal to 1 corresponds to omega equal to 2 pi by 7. And similarly, k equal to 4 corresponds to omega equal to 8 pi by 7. So similarly, this omega plane is discretized to 7 different samples. Rolling out this omega into a linear portion gives the magnitude of this frequency response, where this omega c in our example is pi by 2. So obviously 2 pi by 7 will be lying over here. 4 pi by 7 is greater than 90 degree and it is plotted over here. In this similar manner, we can plot for 0 to 6. We can observe that the same point k equal to 0 is repeating again at 2 pi. So here we take the center of symmetry as here 3 and we observe that this filter is said to be symmetrical. Step number 3, this h of k, IDFT should be applied to obtain h of n, which is the impulse response. So this step depends upon whether the order of the filter is odd or even. If the order of the filter is odd, this particular formula has to be taken, where it ranges from k equal to 0, 1 up to n minus 1 divided by 2. Since it's a symmetrical filter, if you have n equal to 7, it is sufficient you consider the samples only from 0 up to 3, because 7 minus 1 is 6 by 2, 3. It's sufficient to consider the samples from 0 to 3. Similarly, when n is even, it is n by 2 minus 1. In our example, n is odd. Hence, 1 by 7, 1 plus 2, 1 comes from h of 0 value. If you substitute in our h of k, we'll be getting h of 0 as 1. 2 summation k equal to 1 to 3, real part of, substitute the value of h of k, which is nothing but e power minus j 6 pi k by 7, e power j 2 pi k n divided by 7. So 1 plus 2, substitute, you can get real part of this is nothing but cos. Now we need to simplify this h of n for different values of k. So now we obtain for a linear phase FAR filter, since it is symmetrical, h of n is equal to h of n minus 1 minus n. So for n equal to 0, we get h of 0, which is nothing but h of 6. 7 minus 1, 6 minus 0, h of 6. Substituting in this previous equation for n equal to 0 and simplifying this leads to h of 0 values. Similarly, h of 1 will be equal to h of 5, h of 2 will be equal to h of 4, and h of 3 will be equal to 0.4283, which is nothing but the point of symmetry. So step number 4 is to finally realize the transfer function of this filter based on the filter coefficients. So we know the formula for Z transform, h of z equal to summation n equal to 0 to n minus 1, h of n z power minus n. So substituting for n is equal to 7, we obtain h of 0 equal to this equation. We are exploiting the symmetrical property of the filter coefficients, where h of 0 will be equal to h of 6, h of 1 will be equal to h of 5, h of 2 will be equal to h of 4, and h of 3 will be the point of symmetry. So applying symmetry and grouping, we get h of 0 into 1 plus. This equation is realized. This equation can now be transformed into our FIR filter structure. So we can see that here it is going to be x of n. So at every point here you can see that the first one is h of 0 into 1 plus z power minus 6. So it is nothing but your input over here plus the same input is delayed by z power minus 6. So there are 6 delays involved, and the output of the sixth delay and initial input x both are added together and multiplied with h of 0 to give what is called as y. H of z can be written as y of z divided by x of z. So cross multiplying with this. Similarly, this particular term can be realized as z power minus 1 and then z power minus 5, which is 3 delays. Then it is the fifth delay and added together. In the same manner, if we realize, we can obtain the final response y of z. Final point to be noted down here is the magnitude response is symmetric about pi, like what we have seen in our example. Whereas when you try to plot the phase response of this FAR filter, it is observed that it is anti-symmetric about pi. So you can see that the phase varies in linear fashion, but with the point as pi, it is anti-symmetric about pi. Thank you, students.